In the last class, we have mentioned that the oblique shock and expansion theory can be used to construct many important aerodynamical problems, particularly for the geometries which have straight segments. The most important aerodynamical problem, of course, flow past an airfoil and wing, and since the airfoil and wings are very thin, it is customary to assume the wing and airfoil to be flat plate, and flat plate airfoils are very widely analyzed and always taken as the first problem in aerodynamics of wings and airfoils. So, let us consider a supersonic flow past a flat plate, say at an incidence of alpha. That is, let us consider a flat plate of chord C, set at an angle of attack alpha. The chord is C, and let us consider a supersonic stream is approaching this airfoil. We will consider this angle of attack is such that even after the disturbance created on this free stream, the flow remains supersonic always. Now, since there is no upstream influence in a supersonic stream, the streamlines ahead of this plate remain straight and the upper surface flow is independent of the lower surface flow. Now, the flow on the upper surface turns, and since it is an expansive turn, it turns through an centered expansion fan. It turns through a centered expansion fan, and the Mach number increases, pressure decreases downstream or on the surface of the plate. On the plate being straight, there is no further change in the properties. So, if we consider a particular streamline ahead of this, which is straight, now turns and become parallel to the flat plate surface. Now, coming to the trailing edge, this flow need to turn so that it is parallel to the free stream, and obviously, this turn then in opposite direction and will be achieved through a shock. And the streamline will now become parallel to the free stream. On the lower surface, the reverse happens. The flow undergoes again a turn of angle of attack alpha, but through a shock. And at the trailing edge, again it turns by an centered expansion. And a lower surface streamline can be now, knowing the amount of turn alpha and knowing the Prandtl-Meyer function nu upstream, corresponding to m1 and alpha, we can see what is the Prandtl-Meyer function here. So, knowing nu 1, we can find nu 2 here, or nu 2 is simply nu 1 plus alpha. Where alpha is the magnitude of the angle of attack. Now, knowing nu 2, this of course gives us the Mach number m 2, and using isentropic relation P 2 T 2 from isentropic relation, and again knowing the flow turning angle alpha here and the Mach number ahead of this shock m 2, using the m theta beta relation or the m theta beta chart, we can find the wave angle corresponding to this shock, and once that beta for this shock is known, we can calculate the pressure, temperature, density, all other properties downstream. The pressure of course should be the upstream pressure. Similarly, on the lower surface, knowing m 1 and the flow turning angle theta, we can find out the wave angle beta and the downstream Mach number here, let us call that to be m 3 and P 3. The pressure will be higher here, and again knowing m 3 and the turning angle, we can also calculate the downstream flow properties. Now, looking to the pressure distribution over the airfoil, we see that ahead of the flat plate, the pressure is P 1, and then on the upper surface pressure is reduced to certain value P 2, while on the lower surface the pressure is increased to a value P 3. So, what you see that there is higher pressure on the lower surface and lower pressure on the upper surface. However, the flat plate being straight over this, the pressure is uniform over the entire plate. So, consequently, there is a lift force acting on this airfoil. The lift force L is now given by P 3 minus P 2 into C cos alpha, of course, per unit span. And this can be approximately written as P 3 minus P 2 into C for small alpha. We can also see that there is a drag force given by P 3 minus P 2 into C sin alpha which again is approximately P 3 minus P 2 into C alpha for small angle of attack. Coming back to this flow problem again, you see that the lower upper surface flow first encounters an expansion wave, expansion fan, through which its Mach number increases, and the shock is at upstream Mach number of m 2, which is higher than m 1. While on the lower surface, the flow encounters the shock first at a Mach number m 1 and an isentropic expansion fan at the trailing edge, which increases the Mach number again back to m 1. Now, the upper surface flow and then lower surface flow experiences the shock at different Mach number, the upper surface shock being at higher Mach number, and consequently for same amount of turning this will be a stronger shock. So, on the upper surface we have a stronger shock compared to the shock on the lower surface. As a consequence, the entropy change experienced by the upper surface flow and the lower surface flow are not equal, and hence there is a difference in the entropy level on the upper and lower surface flow, and consequently we will have a slip stream. And as we have seen in earlier cases that on the two sides of the slip stream, other than the pressure and flow direction, the other flow parameters can have different value. The entropy values are obviously different, as you have seen. Similarly, the density and the velocity, they will also have different values, or as if this works as a tangential vortex sheet, which creates a difference in tangential velocity across it. Now, this is the flow behavior near the flat plate. However, if we try to look to the far field, then we can see that these expansion fan may interact with the shock. That is, as you have seen earlier, that there might be shock expansion interaction. Consequently, this shock may become curved and there will be reflected surface, reflected flow pattern, and the far field flow pattern is likely to be and consequently the shock is likely to be curved we show the slip line, and these then can reflect back and again this reflected wave So, you see that in the far field and particularly flow downstream is quite complex with having shock expansion interaction and then reflection and again interaction of those reflected waves and so on. However, in these cases these reflections will not be incident on the flat plate itself, and consequently the flow over the flat plate or in the immediate vicinity of the flat plate will remain undisturbed of these shock expansion interaction, and the lift and drag of course, for inviscid flow are quite accurate and exact. One very important thing we notice here that in a supersonic flow even where there is in two dimensional case there is a finite amount of drag force. We have seen that in subsonic two dimensional inviscid flow there is no drag force. The drag force in inviscid flow can come only in 3 dimension, which is lift induced drag. However, in case of a supersonic flow we see that there is a drag in 2 dimensional inviscid flow as well. This drag is known as the wave drag. This drag, which is in this case as P 3 minus P 2 into C sin alpha. This drag is called wave drag. Inviscid supersonic flow. So, this is a special feature of supersonic flow that there is a drag even in 2 dimensional inviscid flow, and this drag is called the wave drag. This is due to the presence of waves in supersonic flow, this drag comes in, and this will always be present in a supersonic flow. Now, let us consider another very important supersonic airfoil, which is the diamond section airfoil. Let us consider we have a symmetric consider a symmetric section symmetric airfoil at 0 incidence. However, the construction of the flow will be same even if the airfoil is not symmetric and the angle of attack is non-zero. Let us consider this angle to be epsilon and epsilon, that is total 2 epsilon angle. and same here is also 2 epsilon. Let us consider again a supersonic free stream. Now, see that as you have discussed earlier, that here the flow will turn and become parallel to the wall through a shock, and on the both surface this will be a shock in this case. However, whether it is a shock and expansion fan, that will depend on the amount of turn that the flow will undergo. So, in case this airfoil at an angle of attack and that alpha is such that this becomes an expansive turn, in that case there will be an expansion fan here. So, subsequently of course, here the flow will turn again through an expansion fan, and then again it will turn here by an oblique shock. Of course, you should remember that we are considering the flows where even after decrease in Mach number through a shock, the flow still remains supersonic. That is, we are always considering only weak solutions. So, if we consider a streamline upstream of the Mach number, upstream of the airfoil, the streamline is straight at a Mach number m 1 with pressure P 1. At the first shock, it turns and become parallel to this straight segment. Through the expansion fan, the flow again smoothly turns and become parallel to this downstream surface. Again it turns through the oblique shock and become parallel to the free stream. Exactly identical happens at the lower surface. Now, if the flow is symmetric, or if the geometry is perfectly symmetric, then the Mach number at the corresponding segment on the upper and lower surface are exactly identical, and all the shocks occur at same Mach number, and the entropy change undergone by this flow on the upper surface as well as on the lower surface are identical. Hence, in the wake the flow is have same entropy and there is no slip stream here. However, if there is asymmetry in the geometry which will cause asymmetry in the flow, then there will be a slip stream from the trailing edge whose direction will be determined by the total turn that the flow undergoes on the upper surface and on the lower surface. Now, let us say the Mach number here is m 2 and the pressure is P 2, and here it is m 3 and P 3, and here it is m 4 and P 4, which should be P 1, this P 4 should be P 1. Now, the pressure distribution, if we plot on the airfoil surface upstream of the geometry, the pressure is uniform at P 1, At the shock, pressure jumps to P2, and on the surface pressure changes to pressure remain constant at P2. On the downside face, downstream face, the pressure is again uniform at P3, but which is much lower. Remember, the turning here is the double of the turn here. Now, if the geometry is symmetric and at 0 angle of attack, the flow is also symmetric on the upper and lower surface, as we have discussed, and consequently the pressure on this face is also equals P2 and pressure on this face will also equals P3. Consequently, there is no lift force in this case. The pressure distribution having upper and lower surface symmetry, no lift force. Pressure distribution has, however, since there is an overpressure on this forward face and lower pressure under pressure on the downstream face or the rearward face, overpressure on the forward face, overpressure on the forward face, and under pressure on the rearward face. This results in a drag force. Now, if this maximum thickness we denote it by T, if we denote the maximum thickness by T and the chord by C, then the drag force can be written as this drag force D, and this drag force can be written as P2 minus P3 into a component of P in the drag direction into T per unit span. And that is equal to P2 minus P3 into T for small epsilon. Now, let us consider a curved airfoil section. Consider a curved airfoil section. For supersonic flow, the airfoils are usually having sharp leading edge, so that the shock remain attached and there is no detached bow shock, and hence no large pressure loss. So, considering a carved airfoil, now in this case there is a shock attached at the nose. However, subsequently there is a continuous expansion occurs along this surface, and consequently these, in this case these expansions are very close to the shock, and they will interact, and consequently the shock will become carved. At each interaction the shock strength will decrease, and due to this attenuation the wave angle will also change, and the shock will continuously bend. And the pressure distribution here, you can see that at there is no upstream influence as in case of supersonic flow. So, the pressure up to the leading edge remains at P 1, and at the leading edge there is an increase in pressure due to the shock. However, then the pressure continuously falls, and again it increases to the free stream pressure. The shock at the trailing edge will also be carved, because these interaction of these expansion fan and shock, expansion waves and shocks, there will be a reflection. These reflections will definitely hit or interact with the trailing edge shock. Not only that, even these reflected waves may interact on the airfoil surface, and through these interactions there will be continuous change in entropy and also of bodicity, and the flow will be rotational, even though this is inviscid flow. Now, in this case, of course, because of this continuous change in pressure, it is not straightforward to apply this shock expansion theory. And using this exact shock expansion results, we cannot compute the properties on the surface of these airfoils. And to do this, we need to simplify the shock expansion theory or results of the shock expansion theory. So, we will and which gives us a supersonic thin airfoil theory. As you have seen that if we apply this shock expansion theory, we get exact result. However, this shock expansion theory is not very convenient for a carved airfoil section, and that is the shock expansion theory result cannot be expressed in a concise analytical form, and hence not suitable for various application, particularly having carved surfaces. Now, we can linearize the shock expansion theory for a thin airfoil, because when you have a thin airfoil theory at small angle of attack, for a thin airfoil theory, for a thin airfoil at small angle of attack, the flow deflections are always small. Flow deflections are always small. Consequently, that we can use that basic pressurized relationship, approximate pressurized relationship Now, when the turn is very small and the pressure rise is also small, the flow deflection is also small, and the difference in pressure ahead and behind the wave is also not large, and consequently P 2 and M 2 are, that is the pressure and Mach number behind the wave is not much different from P 1 and M 1, that is pressure and Mach number ahead of the wave. And for small deflection shock is weak and M 2 P 2 are close to M 1 P 1. Using this approximation, we can even write that with this we can write delta P by P 1 is approximately equal to gamma M 1 square by now theta is now relative to free stream. Now, the pressure coefficient is defined as P minus P 1 by half rho 1 U 1 square, that is delta P by gamma by 2 P 1 M 1 square, that is that is pressure coefficient at any point is expressed in terms of the slope of the local position. So, this is in a sense a local inclination theory, which says that the pressure coefficient at any point on a thin airfoil is simply given by the free stream Mach number and the local flow inclination. Now, considering if we apply this to a flat plate, this to a flat plate at angle of attack alpha, the pressure coefficient on the upper surface is minus 2 alpha by and pressure coefficient on the lower surface is consequently, the lift coefficient CL is P L minus P U into C cos alpha by So, for flat plate at small angle of attack alpha, we can see that lift coefficient according to this linearized theory or thin airfoil theory in a supersonic flow is 4 alpha by root m1 square minus 1, or the lift curve slope is while the same result for incompressible thin airfoil theory incompressible thin airfoil theory is 2 pi. We also see the drag coefficient so that gives the wave drag coefficient from thin airfoil theory. we can clearly also see that the aerodynamic center in this case is at the mid chord. Similarly, if we consider the diamond section airfoil, for the diamond section airfoil, the Cp is given as plus minus 2 epsilon by root over m1 square minus 1 plus is on the front face and similarly minus is for the rear face. And this gives the pressure difference on the front face and the rear face to be front face minus rear face into half and using the formula that I have derived earlier, the drag is approximately P 2 minus P 3 into T, which is P 2 minus P 3, and this T can be expressed in terms of epsilon into C, and substituting these pressure coefficients, this becomes 4 epsilon square by root over m1 square minus 1 into half rho 1 u1 square into C, and this implies C d equal to now for a general curved airfoil, similarly, we can express the pressure coefficient in terms of the local surface inclination, and in terms of the local surface inclinations, pressure coefficient on the upper surface is and on the lower surface it is if x axis is aligned with chord, then CPU the lift force can be obtained as half rho 1 u 1 square into 0 to c and drag force can be obtained as half rho 1 u 1 square into 0 to c . And similarly, the lift coefficient can be 1 by c 0 to c CPL minus CPU dx and the wave drag coefficient similarly will become 0 to c CPL minus DYL dx plus PU DYU dx. In this case, of course, we have assumed that the x is general usual horizontal direction, not aligned with the chord, and the appropriate relations can be used if we align the x with the chord. And since the average camber if the average camber over the entire airfoil is 0, the lift coefficient airfoil with average camber 0. In that case, this lift coefficient will again come to 4 alpha by root over m1 square minus 1. However, C d will become as 4 by root over m1 square minus 1 alpha square plus square of average camber plus average thickness. So, to summarize, we have first constructed flow problem for some simple two-dimensional geometrical configuration which have state geometry, and we have seen that for these cases we can apply our exact shock expansion theory to find the forces acting on these airfoils. However, since exact shock and expansion theory results are not amenable to concise analytical form, we have seen that these exact relationship are not straightforward or not conveniently used for geometry with curved section, and for such a situation we have linearized or made approximation of thin airfoil or thin geometry set at thin and small angle of attack, and we have approximated our shock expansion theory results and seen that the pressure coefficient at any point on a geometry is a function of the local surface inclination, and using that theory we have again computed the lift and drag coefficient of some simple geometries. However, this must be remembered that these are based on the assumptions that the flow pattern remains simple, at least on the surface, and very close vicinity of the geometry, that is the reflected waves, they are not incident upon the geometry, and if the reflected wave is incident on the geometry, then of course the simple analysis is invalid, and more complex analysis or in general numerical simulation of the complete flow field equations are essential.